So after we find the critical section which has the maximum moment, you can find the stress corresponding to this bending moment. If you have only moment about z-axis, which is the case in this problem, then it's gonna look like this. So if the cross section is look like something like this, where this axis is z, this axis is y, this equation is gonna give me the normal stress due to the mz. As you see, the forces applied here is making a rotation about z-axis. It's making a bending about z-axis. If you have moment about y-axis, which is trying, just think about applying force in this direction, it's making bending about y-axis, then z is going to change to y is going to change to z, and izz is going to change to iyy. But this one you don't need to have negative sign, because on the opposite positive side of the z, you will get the tensile, which is true. And what else? That's all. I mean, this point is the neutral, the location of the neutral axis. So we know how to find the location of the neutral axis, but by looking at table A18 for some common cross section. So it's you just need to find the centroidal axis of cross section. For circle, it's going to be at the middle. For this, it's going to be at the middle. With this one, with the hollow, it's going to be at the middle. For some more complicated cross section, you are going to have something like this. But what if you have a beam like this? The cross section look like something like this if you look at the cross section from this side. So if this is under some load, we would like to find the normal stress due to the bending moment coming from this loading. So to do that, we should use that equation that we derived. But before we start, we need to find the location of the neutral axis. So let me, I will draw the dimension . So the dimension of this cross section is given. We know that it's made of, this one is just, this one is 80, this one is 122. we need that this beam is made of a material which can support normal stress maximum equals to 150 megapascal. So if the stress applied to this cross section is exceed 150 MPa, it's gonna fail. So we would like to know what would be the maximum phi and max. What would be the maximum bending moment that we can apply to the cross section? The first thing that you need to do is finding the location of the neutral axis. If this is X, if this is Y, I would like to find the location of the neutral axis. Due to the symmetry that we have about this axis, you see we have symmetry if I draw a vertical line at the middle. I know where should I put the Y axis for the neutral axis. So I know it's going to be at the middle. So the only thing that I need to find, how far should I go up to draw the location of the neutral axis in X direction. So I know that I'm looking for Y bar. Y bar. And if I ask you what would be the X bar is going to be is located at 40 millimeter. I already know that. So X bar is 40 millimeter, but Y bar can be obtained by applying this equation. We have three cross sections. One is here, second, and third. This equation says to find the Y bar, you need to multiply A1 multiplied by Y bar 1. Where is the Y bar 1? For this rectangular, it's going to be at the middle. Y bar 1 would be 120 divided by 2, 60 millimeter. For this one, Y bar 3 is 60 millimeter, and for this one, Y bar 2 is 8 millimeter divided by 2 is 4. Divided by summation of the A. What would be the total cross section? So A1 is 8 millimeter divided by multiplied by 120. A2 is from here to here is 64 millimeter. So this cross section is 64 times 8. And A3 is going to be the same as A1. They are identical. Just plug in the numbers. A1 is 8 times 120 times Y bar 1, which is 60, plus A2, 64 times 8 multiplied by 4, which is Y bar 2. And the last one is same as the first one. I'm just repeating. Divided by 8 times 120 plus 64 times 8 plus 8 times 120. This is how you can find the Y bar. If you do the calculation, you will find 48.21 millimeter. So it tells me I should move this axis of x up to 48.21 and draw this. So the location of neutral axis is going to be right here. Now, we know that normal stress is M times Y divided by IZZ. I know that the maximum normal stress is 150 megapascal. This is the maximum allowable stress. I'm looking for M max. I should calculate Y and IZZ, I with respect to the neutral axis. Which Y should I put? I should see if this line has a greater Y or this line has a greater Y. So from here to here is 48.21. What would be this distance? 120 minus 48.21. 71.79 millimeter is going to be the distance of the top line and the cross section. So this one is greater than this one, so it means the stress at this line is going to be greater than stress at this line. I'm just talking about the magnitude, not the tensile or compression. So, but magnitude-wise, Y max is 71.79. Good. We are not done yet because we need to find IZZ with respect to, this is, I mean, if this is the axis and labeled as an X, with respect to Z neutral axis. How can I find the second momentum area with respect to this axis? We are using the parallel axis. I with respect to ZZ is going to be I with respect to I1 with respect to ZZ plus I2 with respect to Z axis plus I3 with respect to Z. I mean I1 for first cross section, I2 for the second cross section, and I3 for the third cross section. I1ZZ, I would like to find the second momentum area of this cross section with respect to this line, this axis, which has a distance of 48.21. The parallel axis tells me it's going to be I1ZZ with respect to its neutral axis plus the distance squared times A1. So if this is cross section 1, I know that the I1 ZZ with respect to its neutral axis is gonna be, this is B, this is H. B times H power 3 divided by 12, which is H times 120 power 3 divided by 12. What is D1? The axis that I have is locating at the distance of 48.21. This is the axis that I would like to find the neutral second momentum area with respect to that. What is the distance between these two? This is 60, this is 48.21. D1 is 60 minus 48.21. So to find I1 ZZ, I need to plus this distance, which is 11.79 times area. This is square, 11.79 square times 120 times 8. 120 times 8. So it's going to give you the second momentum area of this cross section with respect to this neutral axis, which is equals to 128, 549, five, 4, 44 millimeter power 4. So I'm done with the first term. Second term, I2 ZZ. It's going to be I2 with respect to neutral axis plus D2 times A2, D2 squared times A2. I2 equals to, I'm talking about this. With respect to its neutral axis, it's going to be 64 times 8 power 3 divided by 12. D2 would be this distance. From here to it is 48.21 minus 8 minus 4 millimeter, which is 44.21. So just plugging the number there, and you will get 103, 447 millimeter. Make sure that you follow the step, because the one of the homework problem is asking you to do the same thing for a given cross section.
Why do you have the D squared times
Okay, it's a parallel axis theorem. We know that if this is a cross section that we have, and if this is the axis, I with respect to z axis is b times h power 3 divided by 12.
Oh, okay, I see.
If the axis is different somewhere here,
Right.
Then you need to consider the distance and a square multiplied by A.
Yeah.
So it's another reason that we need to find the location of the neutral axis first. Any question on this so far? For this cross section, these two are identical. So if I do the same things that I did for the first cross section, I will get the same I1ZZ for I3, the same distance, and same cross section. So I'm gonna repeat myself to find this. So the total I, which I have here, is gonna be the summation of all three. 2 times this not that, and plus 103,447, which is gonna give me 357,4334, and the unit is millimeter over 4. Now I can plug in the numbers here. I'm looking for M max, so I leave it there. The Y, what would be the maximum Y? I just calculated here, 71.79. I changed the unit to meter, so it's gonna be 71.79 10 power negative 3 divided by I, it's a unit millimeter. If I want to change it to meter, I should to multiply this by 10 power negative 12, because 1 millimeter is 10 power negative 3 meter. 1 millimeter power 4 is going to be 10 power negative 12. So whatever I have here, solve for M max. M max is gonna be 7,468 Newton meter. So for the beam with this cross section, you cannot exceed the bending moment at the cross section. This moment.
First, when we're calculating the distance, are we calculating from the neutral axis from the individual item to the neutral axis?
Yes, in
Okay.
neutral axis to neutral axis.
Okay. All right.
Yes.
So the center.
Center to center.
And then for, how did you get to the power of negative 12? I'm sorry.
The unit is millimeter power 4. I just need to change it to meter power 4.
To the power. Okay.
So each millimeter is 10 power negative 3. If you make it power 4, it's going to be negative 12. Meter square is going to be 10 power negative 6. Meter power 3, 10 power 9. And meter power 4 is going to be 10 power negative 4. Any question on this? So you cannot exceed the moments, the maximum bending moment on the critical section than this. If I ask you what would be the normal stress on this line, the only thing that you need to do, you have moment, plug in here, you have IZZ, it's going to be there. Just you need to plug in Y by 48.21. So you will get the normal stress at this line. And at this line, it's obvious that you will get 150 megapascal. Any question? All right, let me work on one simple design problem as well before we move on transfer shear. Suppose we have a simply supported beam with circular cross section. Z-axis, Y-axis, and X-axis. So the cross section is circular. The length is 18 inch. At the location of 6 inch, we have 400 pound 6 inch. At the location of 8 inch from the first force, we have 150 pound, and the rest is 4 inch. So we have this simply supported beam. It's made of material that we don't want to have normal stress exceed 10,000 psi, pound per square inch. So we don't want to have normal stress exceed 10,000 psi. How do I know that? Because I know what would be the material of this beam, and based on the material, it shouldn't exceed 10,000 psi. Now the question is, design the radius of cross section to support this loading. So basically we are looking for D. So we have some load applied here. So due to this loading, we are going to have bending moment. Bending moment is making the normal stress. I should find the critical section, and then I do the analysis. I do the design based on that critical section. How can I find the critical section? I'm drawing the bending moment diagram. First, I need to find the reaction. I'm just writing the reaction here. R1 is 300. I don't drive the value, but you know how to do that. 300 and 250. And then draw the bending moment diagram. So the bending moment diagram is going to look like this. By looking at this, you will notice that if this is point B, A, B, C, and D, section B or the location of this is going to have the maximum bending moment. The value is 1,800 pound-inch. So the critical section is located at point B, which is 6 inch from point A, and the magnitude of the moment is 1,800. So M sigma is going to be M Z, the direction of the moment is about z-axis, times Y max, or C, divided by I with respect to z-axis. This is z-axis, this is Y. So what would be the Y max? The Y max in the circular cross section is going to be on the top, equals to the half of the diameter. So it's going to be mz times d over 2, and iz for the circular cross section is pi d power 4 divided by 64. I with respect to z, what would be the maximum y? It's d over 2. It's going to give me 32m divided by pi d power 3. The moment is 1,800. 32 times 1,800 divided by pi d power 3. What would be the maximum normal stress is 10,000. Solve for d. So d power 3 is 32 times 1,800 divided by pi times 10,000. Then we can find d equals to 1.22 inch. If you want to use the standard value by looking at the table, the closest value is 1.25 inch. So we can round it to 1.25. If you want to make an order, to order the beam with the diameter of 1.25. Although the calculation showing 1.22, but this one exists in the market. Any question on this? This one was a simple problem, but the idea would be the same for more or less complicated problems. We find the critical section, we find the stress at the critical section, and depending on the information that we are given, we are solving for on given values. Here I ask you for diameter. I could provide diameter and ask you to find the maximum normal stress. So if we have a beam which is under some loading, you will see that we are going to have bending moment, which makes normal stress. Also, due to the transverse force or shear force, we are going to have shear transverse shear stress. we would like to study this. So if I have f some x this distributed load, this is the x-axis, y-axis, and z-axis. So we know how to find the normal stresses due to the bending moment. Now we would like to know what would be the transfer shear stress due to the transfers or shear forces. I'm looking at the cross section. If I look from this side, I will see z-axis in this direction and y-axis in this direction. You draw the shear force diagram, find the critical section, the section which has the greatest shear force, if you want to know what would be the maximum transfer shear. So you find the critical section by looking at the shear force diagram to calculate the maximum shear force and transfer distance. Suppose this length is B, this length is H, and half of that is going to be H over 2, or we call, since the book labeled as C, I labeled as a C as well. But it's going to be half of the H. C equals to half of it. For this point A, I would like to find the shear stress at point A due to this shear force. Point A has a distance of y from the neutral axis. The shear stress at point A, which has a distance of y from the neutral axis, is going to be this. What would be the shear force applied to this cross section? We can find it by looking at the shear force diagram, times Q, I will talk about Q, divided by I with respect to Z. The shear force is Z direction, the I should be about Z, the V is about Y direction, the I should be about Z direction. So the shear force in this case is about Y direction, but the I that you are using, it should be about the other axis, which is Z, times B, this length. So V is given, you know how to find I, the B is the dimension of this length, you know that. The only thing left is QA. QA I is the second moment of area. Q is the first moment. Second moment means integration of y squared dA. First moment, this y squared is going to change to y dA. We need to find the first moment of area on the top of point A. So I draw a line parallel to z-axis and do the first integration of the area for this part of the cross section. Y dA means the integration from Y to C, from this point to this point. Whatever the area between this point should be covered in So this is how you can find the shear stress at any desired point. So if I have shear force in z direction, not y direction, it's possible you have seen a problem like this when we worked on this type of the problem. Here, the shear force is about y-axis. Right here, the shear force is about z-axis. So if I have something like this, then the shear stress at point A is going to change. V is going to change to Z. I is going to change to Y. This B is going to change to H. And this Q prime A is going to change to this cross section. I mean, these parts of the cross section. Now, if I have point 1 here, point 2, point 3, 4, 5, 6, and 7. Let's put point 8 and 9 here. At which point I'm gonna see the maximum shear stress. Which point, based on what I explained here, which point is gonna see the maximum shear stress, and which point is gonna see the zero. It just under, I would like it's under shear force, something like this. So it's making transverse shear. Now I would like to know which point is gonna see the maximum shear stress, which point is gonna see the zero shear stress. If I ask you which point is gonna see the maximum bending moment, you know where is it, but it's a transverse shear. Number 42. Number 10. Number 10. number 7. What
I
is-
have no clue.
So the shear stress has 1, 2, 3, 4 terms. Which terms would be the same for all points?
B.
B is the same. Okay. What about I?
I and Q.
Okay. And Q you said? It's not
Or
true.
no, because that changes.
But shear force and this cross section has the same value. You just look at the shear force diagram, you figure out this section has the maximum shear force. So all points on that cross section they are gonna see the same shear force. The only thing which is different is Q. So if I choose point A here, Q is gonna be the integration about this section. If I choose point B here, the cross section is gonna be greater. So if I pick point in this line, it's gonna be Q is gonna be 0. So but there is no area for Q. So all points on these two lines they are gonna get 0 shear transfer shear. And all points in 6, 7, and 3, they are gonna see the maximum cross section, which is gonna get the greatest shear transfer shear. Does it make sense? This table for different cross section has calculated the maximum shear force. It has calculated this integration for this line, and you can see the maximum shear stress. Maximum transfer shear stress for rectangular cross section is 1.5 times V over L. For the circular cross section, it's going to be this. For this cross section, you will see there, and for hollow, you can find over there.